In mathematics, a partition of a set is a grouping of the set's elements into non-empty subsets, in such a way that every element is included in one and only one of the subsets. Definition: a partition of a set X is a set of non-empty subsets of X such that every element X in X is in exactly one of these subsets. Equivalently, a family of sets P is a partition of X if and only if all of the following conditions hold. P does not contain the empty set. The union of the sets in P is equal to X. The intersection of any two distinct sets in P is empty. In mathematical notation, these conditions can be represented as if and then, whereas the empty set. The sets in P are called the blocks, parts or cells of the partition. The rank of P is X minus P, if X is finite. Examples: every singleton set X has exactly one partition, namely X. The empty set has exactly one partition, namely the empty set. For any non-empty set X, P equals X is a partition of X, called the trivial partition. For any non-empty proper subset A of a set U, the set A together with its complement form a partition of U, namely A, U minus A. The set 1, 2, 3 has these 5 partitions. 1, 2, 3, sometimes written 1, 2, 3, 1, 2, 3, or 12, 3, 1, 3, 2, or 13, 2. 1, 2, 3, or 1, 23, 1, 2, 3, or 123. The following are not partitions of 1, 2, 3. 1, 3, 2 is not a partition because one of its elements is the empty set. 1, 2, 2, 3 is not a partition because the element 2 is contained in more than one block. 1, 2 is not a partition of 1, 2, 3 because none of its blocks contains 3. However, it is a partition of 1, 2. Partitions and equivalence relations. For any equivalence relation on a set X, the set of its equivalence classes is a partition of X. Conversely, from any partition P of X, we can define an equivalence relation on X by setting X tilde Y precisely when X and Y are in the same part in P. Thus the notions of equivalence relation and partition are essentially equivalent. The axiom of choice guarantees for any partition of a set X the existence of a subset of X containing exactly one element from each part of the partition. This implies that, given an equivalence relation on a set, one can select a canonical representative element from every equivalence class. Refinement of partitions. A partition alpha of a set X is a refinement of a partition rho of X, and we say that alpha is finer than rho and that rho is coarser than alpha, if every element of alpha is a subset of some element of rho. Informally, this means that alpha is a further fragmentation of rho. In that case, it is written that alpha rho, this finer than relation on the set of partitions of X, is a partial order. Each set of elements has a least upper bound and a greatest lower bound, so that it forms a lattice. And more specifically, it is a geometric lattice. The partition lattice of a 4-element set has 15 elements and is depicted in the Hasse diagram on the left, based on the cryptomorphism between geometric lattices and matroids. This lattice of partitions of a finite set corresponds to a matroid in which the base set of the matroid consists of the atoms of the lattice. The partitions with singleton sets and 1-2-element set. These atomic partitions correspond one for one with the edges of a complete graph. The matroid closure of a set of atomic partitions is the finest common coarsening of them all, in graph-theoretic terms. It is the partition of the vertices of the complete graph into the connected components of the subgraph formed by the given set of edges. In this way, the lattice of partitions corresponds to the graphic matroid of the complete graph. Another example illustrates the refining of partitions from the perspective of equivalence relations. If D is the set of cards in a standard 52-card deck, the same color as relation on D, which can be denoted ~C, has 2 equivalence classes. The sets red cards and black cards. The two-part partition corresponding to tilde C has a refinement that yields the same suit as relation tilde S, which has the four equivalence classes: spades, diamonds, hearts, and clubs. Non-crossing partitions. A partition of the set n equals 1, 2, n, with corresponding equivalence relation tilde is non-crossing provided that for any two cells C1 and C2, either all the elements in C1 are less than all the elements in C2, or they are all greater than all the elements in C2. In other words, given distinct numbers a, b, c and n, with a less than b less than c, if a tilde c, it follows that also a tilde b and b tilde c, that is b is also in C. The lattice of non-crossing partitions of the finite set has recently taken on importance because of its role in free probability theory. These form a subset of the lattice of all partitions, but not a sublattice, since the join operations of the two lattices do not agree. Counting partitions. The total number of partitions of an n-element set is the Bell number Bn. The first several Bell numbers are B0 equals 1, B1 equals 1, B2 equals 2, B3 equals 5, B4 equals 15, B5 equals 52, and B6 equals 203. Bell numbers satisfy the recursion and have the exponential generating function. The Bell numbers may also be computed using the Bell triangle, in which the first value in each row is copied from the end of the previous row, and subsequent values are computed by adding the two numbers to the left and above left of each position. The Bell numbers are repeated along both sides of this triangle. The numbers within the triangle count partitions in which a given element is the largest singleton. The number of partitions of an n-element set into exactly k non-empty parts is the Stirling number of the second kind S.